Hello everyone, welcome back. So we have been discussing our acid and base systems in the previous lecture sessions, right? And we have been delving into greater detail with respect to the applications. And the applications anyway that we have been looking at was given initial concentrations of various acids or bases, what would be the equilibrium concentrations, and obviously what would the pH at equilibrium, right? This is what we have been looking into, and we looked into them in greater detail. And then we moved on to log C pH graphs, right? And as we discussed, the log C pH graphs will give you an idea about how the system changes with pH, right? And again, they were widely used in the past, and I guess still widely used in India as of now. But with your particular knowledge or background now that you are gaining with respect to be able to use VMINTEQ, right? And also with respect to the mathematical tools available such as Excel and such, you can do away with what is it now, the log C pH diagrams. But again, still whenever you are looking for a snapshot of the system, and if you have one readily available, I am talking about a log C pH graph here, you can always have a look at it, right? So again, now we are going to move further, and we are going to look at a particular acid base system pardon me, which we come across everywhere, right, in the natural systems and in the engineered systems, right? And obviously this is ubiquitous, right, or omnipresent. And what does that mean? It's something that's present everywhere and in considerable concentrations, right? And if you haven't guessed it already, it's going to be the carbonate system. And why carbonate specifically? Because subsurface you have deposits of calcium carbonate, and in the atmosphere you have carbon dioxide. So both of these more or less will affect your carbonate system, and thus because both these deposits and the carbon dioxide in the atmosphere are ever present, that's almost always going to lead to considerable concentrations of your carbonate system, or the carbonic acid, or the bicarbonate, or CO3 2-, right? So we are going to look at this system in greater detail over the next two lecture sessions at least, I believe. So let's move on to what we are going to look at here. So what are some of the species that we look at here, right? So here is the graph that we are going to look at. So we'll come back to this. So the species primarily are CO3 2-, the carbonate. So we are going to identify the species in this acid base system. So there are three major species that we are concerned with that are going to be at equilibrium in your aqueous phase. The first one is the carbonate, the other is the bicarbonate, and the last one is the carbonic acid. And the carbonic acid is obviously going to stay in equilibrium with the carbon dioxide in your gaseous phase. So let's go by one. So CO3 2-, an important source of this is your CaCO3 deposits, right, in the subsurface, or in the ocean and such, or the ocean bed and so on. So in general you will have considerable source of CaCO3. And the second case is going to be, or the second species that we are going to look at is the bicarbonate. And as you see from this particular the speciation diagram here, right, at pH 7, right, and where is pH 7? You see that the bicarbonate is the predominant form of the species that's going to be present, right, or the predominant species in the carbonate system. So again, at natural pH or neutral pH, pardon me, the bicarbonate is a particular ion that you are almost always concerned with, and that's what we see here. Again, let's move on to the last particular species, that's H2CO3, the carbonic acid. The carbonic acid, pardon me. So thus carbonic acid, which is going to be in the aqueous phase, is going to be in equilibrium with carbon dioxide in the gaseous phase, right? H2O, H2CO3, okay, it's balanced. So what does this mean now, let's say, right? Let's say if I have a beaker of water, let's say, and I put it up, or leave it open to the atmosphere, right? What's going to happen now? You have carbon dioxide in the gaseous phase or in the atmosphere all around it. So over some time, let's say a few days or a day, depending upon the temperature and the conditions in that particular room, right, you are going to have an equilibrium between the carbon dioxide in the atmosphere or the gaseous phase and the carbonic acid in the aqueous phase, right. This is the equilibrium, phase equilibrium here again, right. So that's going to be achieved over time, and that's the equation that we are going to look at, H2CO3 here, right. And this is one particular aspect that I want to stress upon. So people might have heard of global warming, right, and you talk about these greenhouse gases, carbon dioxide, methane and so on. But one aspect that's maybe that hasn't received as much attention, but the scientific community is acutely aware of it, is that increasing carbon dioxide concentration. So think of this now, other than the global warming potential, one major aspect that threatens the way of life in our aquatic systems is going to be the pH, or the change in pH, or the drop in pH. So think of this now. So you have your atmosphere, let's say, I'm going to model this with Earth, and these are your oceans, right, and this is your atmosphere. So as the carbon dioxide concentration in your gaseous phase keeps increasing, right, so that's what we are looking at. So obviously there is going to be an equilibrium with the carbon dioxide in the gaseous phase, with the carbon dioxide that is going to be dissolved in your aqueous phase. And obviously, as we just looked at it, carbon dioxide in the aqueous phase is going to stay as H2CO3, or the carbonic acid. So what does this mean now? So as you keep increasing the concentration of your, or the partial pressure of your carbon dioxide, right, what's going to happen now? You are going to increase the concentration of H2CO3 in your ocean. And H2CO3, as we know, right, with our background in the past few classes, is an acid that can donate a proton depending on the pH, right. So what's going to happen here? You are going to decrease the, or have a slight decrease anyway, because we are going to look at the large volumes here, and the pKa2 is relatively high. So anyway, there is going to be a decrease, if ever even a slight decrease, or there has been a decrease of the pH of the oceans now. And the key issue here is that most of the aquatic systems are remarkably, or almost all the aquatic systems are remarkably sensitive to pH or any change in pH. So as the pH drops, let's say even by 0.1, let's say, I think 6.7 to 6.5 or so, let's look at the graph in the next lecture session, or the one after that. So if you look at that, let's say the pH has dropped, or the increasing carbon dioxide concentrations have an effect on the pH of your oceans now, and that has a remarkable effect, or cascading effect on your particular aquatic systems or aquatic life. So that's something that we need to be again acutely aware of, other than just the global warming potential, right. So again, let's come back to our particular cases here. So we are talking about the carbonate system, and why it's ubiquitous, it's present everywhere, and the three species that we in general look at are CO3 2-, the bicarbonate, and the carbonic acid. And as we just talked about, the carbonic acid, right, can stay in the form of H2CO3 itself in the aqueous phase, or as dissolved carbon dioxide, right, dissolved carbon dioxide. So in general, when people talk about carbonic acid, they refer to both the dissolved carbon dioxide and the actual carbonic acid in the water, right. So again, some people use the notation with respect to an asterisk, let's say, right, and I'm referring to, so whenever you see H2CO3 with an asterisk, this is what it means to, right, different what do we say, terms more or less, or terminology. So now we are going to dig further into it. So again, before you go further, this is an acid based system, right. So obviously, what are the major aspects that you need to immediately think of, right? It's going to be the pKa. What is the pKa of this system? And as you see, it's a diprotic acid, it's H2CO3, so it can give out 2 protons depending on the pH. So we also are going to look at the pH of the system, and we are going to look at the 2 acid dissociation constants, right. So as we can see from this particular graph here, it's going to be around 6.3 and 10.3, right, but we are in general concerned with the neutral pH. So as we see, right, at neutral pH, most of it, as in almost 80% of it, as you see, this is the ionization fraction. And what do these ionization fractions give you an idea about? Let's write them down: alpha naught, alpha 1 and alpha 2. That's going to be equal to H2CO3, the concentration, by the total acid, or let me just write total acid here, and we are going to define total acid like we did elsewhere as sum of all the conjugate acid and base species. Right, and alpha 1 will give you an idea about the fraction that's present as HCO3, or the bicarbonate, I guess, HCO3 minus, and alpha 2 is going to give you an idea about the carbonate fraction, or fraction as carbonate, right? Alpha naught, alpha 1 and alpha 2, that's what you see here. So anyhow, coming back to the graph again, at pH 7 we have almost 80% of it as HCO3 minus, and some of it as, I guess, the 20% as your H2CO3, right? This is your H2CO3 graph, and that's what you see here. So the two species of the carbonate system that obviously are present at your neutral pH are going to be HCO3 minus and H2CO3. And obviously, as you see from this particular graph, with respect to the speciation, you see that the pKa 2 is 10.3. So thus the CO3 2 minus is only going to be present in the system at the relatively higher pH, right? And that's a take home message here. So in general, again, we are concerned with HCO3 minus and H2CO3, and mostly with HCO3 minus, right? And this particular bicarbonate ion, or the anion, is going to affect your system in multiple ways, the applications of which we are going to look at further down the line, let's see, right? So obviously, again, we are now going to look at your particular system with respect to predicting the equilibrium values, right, of the various species, or equilibrium concentrations, pardon me, of the various species, given that you have initial concentrations of some relevant components. So let's look at that. So I guess there are two aspects we need to clarify first. One, that we will work it out for a closed system, and why are we working it out for the specific, and I guess the question that should arise is, why are we looking at specifically a closed system, and why are we defining that specifically now, right? As we just discussed in the last few minutes, we see that H2CO3, right, can be in equilibrium, or will be in equilibrium with the carbon dioxide in the gaseous phase. So for example, let's say a solution that has carbonic acid or the carbonate system in it is open to the atmosphere. Let's say it's not closed anymore, but it's open to the atmosphere. So depending upon the relevant concentrations, the carbon dioxide in the atmosphere can either dissolve into the aqueous phase, or the carbonic acid can reach equilibrium or leave the system as CO2 into the gaseous phase again. So let's just try to represent what we have been talking about. So for example, let's say, this is my closed system, and there is a specific concentration here with respect to H2CO3, HCO3 minus and CO3 2 minus, let's see, right? But later on, let's say I open up this system. Do you think the concentrations are going to stay the same with respect to H2CO3, HCO3 minus and CO3 2 minus? No. And why is that? Because the carbonic acid is going to be in equilibrium, right, or the carbon dioxide in the gaseous phase is going to be in equilibrium with the carbon dioxide in the aqueous phase. And what do you see here? So you can either see a transfer of CO2 from the gaseous to aqueous, or vice versa, depending upon the relevant concentrations. And we know that CO2 in the aqueous phase is going to be in equilibrium with H2CO3 in the aqueous phase, right? So that's what we just discussed. So we are going to work it out for two aspects, right? And obviously that's relevant here. So whenever somebody talks about the carbonate system, let's say, or an experiment involving carbonate, you need to look at, are they trying to maintain a particular carbonate concentration, and if so, would that stay in equilibrium with the partial pressure that you would expect in your particular atmosphere, or is it a closed system? If so, then that can be that can go ahead, I guess, right? Anyhow, let's come back to our drawing table here, and we are now working it out for a closed system which is not open to the atmosphere, right? And let us say for the sake of an example, let us say we are adding NaHCO3 and Na2CO3 to our system at relevant concentrations. Let us say these are our recipe species or initial concentrations that we are adding to our system. So, I am adding NaHCO3 and Na2CO3 to the system, and I want to know what is going to the pH and what are the relevant concentrations of your various species, right, that you would expect in this particular system. So, let us look at that. Again, obviously, what are we going to look at? The only way to solve this is going to be the component balance, right. And whenever we look at component balance, we obviously need to define the species. So, for this particular carbonate system, we know that the species are going to be H2CO3, HCO3 minus and CO3 2 minus, the relevant acid and conjugate bases or acids, right. And what else? We are always going to have H plus and OH minus, and here we also have sodium. So, we are also going to have the relevant sodium, the salt here, right. And because this is a closed species, we do not have any other gaseous phase species such as carbon dioxide here. But if it were an open system, which we are going to work out in the next lecture session, or once we are done with this particular aspect, we are going to list, or we need to list, carbon dioxide in the gaseous phase too, right. We are looking at species as in what is the system, or we are trying to analyze the system at equilibrium. So, in this particular case, it is a closed system, it is not open to the atmosphere, third there is no chance of equilibrium with the gaseous phase or no gaseous phase species in our current list, right. And then the key is to choose the components. And what are the components? Obviously, we always try to choose the H plus or the proton, and then the most deprotonated form of the acid, and that is going to be CO3 2 minus, and then the salt or the sodium here, right. And then the formation equations, let's list them out please. The formation equations. So, I am going to first list all the species here. So, I will go with the easier ones first, Na plus, H plus, OH minus, CO3 2 minus, HCO3 minus and H2CO3, right. So, let us see how can I form them. I need one component of Na plus to be able to form Na plus. I need one component of H plus to be able to form H plus. I need a minus one component of H plus to be able to form OH minus. I need one component of CO3 2 minus to form CO3 2 minus. I need one each of H and CO3 2 minus to be able to form HCO3 minus, and similarly I need two components of H and one component of CO3 2 minus to be able to form my particular H2CO3 here, right. So, I am done with the formation equations here. So, obviously, the next step would be the tableau, right. And first here we are going to list the components. They are H plus and what else please, CO3 2 minus and Na plus. Again I am going to list the species. So, Na plus, H plus, OH minus, CO3 2 minus, HCO3 minus and H2CO3, right. In the tableau though, we are also always going to have to list our recipe species or the species that we are adding to the system initially, and these are the two species here. And what are they here please? NaHCO3 naught, or the initial concentration of NaHCO3 that we are putting in, and Na2CO3 naught. So, again we have a closed system. You are adding NaHCO3 and Na2CO3 initially, and that is going to dissolve, or both those compounds are going to dissolve, and then they are going to form new species which we just listed, right. And then here we are trying to predict the concentration at equilibrium, right. So, again let us move on here, and from the formation equations I am going to write this down. It is going to be 1 0 0 0 0 and 0, and it is going to be one component required here and two components of sodium required here, right. And here we have 6 and 6, we are done there. This is going to be 0 1 minus 1 0 1 and 2, and where do we get these values from? Obviously from your formation equations here, right. If you look at the coefficients here of the relevant components, that is where we get them from. and CO3 2 minus, here it's going to be, you need 0 of CO3 2 minus, 0 components of CO3 2 minus to form Na plus, 0 components of CO3 2 minus to form H plus, similarly with OH minus, but with respect to CO3 2 minus you need 1, same case with HCO3 minus and H2CO3. And now coming back to your particular initial species, and for CO3 2 minus it's going to be again 1 here and 1 here, and here it's going to be 1 and 0, right. We'll neglect Na plus because it usually plays little to no further role, right. It's a salt, it doesn't play further role. So we are going to only look at the total component balance with respect to the H and with respect to the CO3 2 minus, right. So we'll work that out further and see how we can analyze the system and understand what are the relevant variables that we are going to have to consider in a closed system, right. So let's move on. Let me see if I can remember. So H total is going to be equal to H plus minus OH minus and what else do we have? I believe we have HCO3 minus, and we will certainly have 2 times H2CO3, and that's going to be equal to what now? Your NaHCO3 naught, right. So let me see if we miss anything. So 1, 2, 3, 4 species are going to contain the component H plus, and that's going to be equal to NaHCO3 naught 1 times, right. And same case with CO3 2 minus. So the CO3 total component balance is going to be equal to what now please? Concentration of CO3 2 minus plus concentration of HCO3 minus plus concentration of H2CO3, and that's going to be equal to NaHCO3 that you are putting in initially, and also the Na2CO3 that you are putting in initially, right. So let's go back, and that's what we have here. So again, what do we have here? We are balancing the component with respect to H here, and the only source of that component is the initial NaHCO3 that you are putting in, and same case we are balancing the CO3 total here in the second equation, and the only source of your particular CO3 in your system is the NaHCO3 and Na2CO3 that you are plugging in initially, right. So here I believe we have around 6 species, but with the sodium balance we were able to, or we can calculate the sodium concentration. So let's remove that as an unknown. So we are left with 5 variables, right. But here we have only 2 component balance equations, thus we have only 2 equations here. So for 5 variables we have 2 equations, and thus we are still looking for the other 3, and obviously here we are looking at the equilibrium solution, right. So obviously the answer lies in looking at equilibrium or the relevant equilibrium constants. So let's try to write down or figure out what the relevant equations are. Obviously because these are acid and base systems, we will have the relevant acid dissociation equations, right. So let's write them down. So you know that H2CO3 can dissociate into what now? H plus and HCO3 minus, you are going to have that, and again HCO3 minus can further dissociate or will stay in equilibrium with H plus and CO3 2 minus, right. H2CO3 will stay in equilibrium with HCO3 minus and CO3 2 minus, and obviously we will always have water dissociation, right, H plus plus OH minus. And so I am going to list the relevant equilibrium constants Ka1 and Ka2 for the 2 protons that can be released by H2CO3, and the water dissociation constant Kw, and the Ka1 is going to be equal to the activity which I am going to approximate by H plus into HCO3 minus by concentration of H2CO3, right. And similarly I am going to have Ka2 equal to H plus into CO3 2 minus by concentration of HCO3 minus, and Kw is going to be equal to the concentration of H plus into the concentration of OH minus, right. So obviously all these need to be defined in terms of activities, right, but we are assuming that the ionic strength is relatively less, and thus we can approximate activities by the concentrations, right. So that's what we have here, and now we have 3 additional equations. right? And so we can solve for our 5 unknowns. Yes. So earlier we had 2 component balance equations, right, or 2 equations from the component balance of H total and CO3 total, and now we have 3 further equations from the relevant acid dissociation constants, right, or equilibrium coefficients too, and that is the general term. Yes. So let us see how we can analyze this further, but for now we are going to concentrate obviously on H total, I guess, right. So obviously as we discussed earlier too, right, and we looked at ionization fractions too, they were derived using these 3 equations, right. So you will have alpha naught is going to be equal to what now, H2CO3 times the concentration of H2CO3 plus HCO3 minus plus concentration of CO3 2 minus, right, and that, as you can see, the denominator, what is the denominator equal to now, right, and that is going to be equal to or similar to this particular variable here. So it is going to be equal to the CO3 total, right, and we are going to use that further. Similarly, alpha 1 is going to be equal to HCO3 minus by CO3 total, and alpha 2 is going to be equal to CO3 2 minus by CO3 total. Again, where do we have this from, CO3 total? It is from this particular equation here, right. Anyway, we are done with that for now. So let us try to analyze or solve for this particular equation here, H total. So I will move on to the next slide here. So H total was equal to concentration of H plus minus concentration of OH minus plus concentration of HCO3 minus plus 2 times the concentration of H2CO3, right. So that is what we have here, and we know that this is going to be equal to NaHCO3 that we had initially, right, and now taking it further or simplifying it so that we have it only in terms of H plus, I am going to have it as Kw by H plus, and HCO3 minus, what do we just have here, I guess, and HCO3 minus we have here. So thus HCO3 minus is going to be equal to alpha 1 into CO3 total, right, that is what we just had looked at in the earlier slide, plus 2 times, and what is H2CO3? H2CO3 we can get from this particular equation here, that is going to be equal to alpha naught into CO3 total, right. So 2 times alpha naught CO3 total. So thus we are going to arrive at H plus minus Kw by concentration of H plus plus alpha 1 plus 2 alpha naught into CO3 total, and thus as we know, anyway for our particular system, because we are initially adding NaHCO3, so that is going to be equal to NaHCO3 naught, right. So again we were looking at the carbonate system. Why? Because that is ubiquitous and that is going to be present in most or almost all your engineered systems and certainly in the natural systems, right, and we try to analyze it for a closed system when it is not open to the atmosphere, and here we have the relevant particular variables. So let us look at what they are. So in general, the relevant variables you need to consider in your carbonate system, which is closed. For a closed system, what are the variables? H total, CO3 total and pH, right, and this and all your variables are going to depend upon these 3 factors, and that is obviously apparent from your particular equation here. So we just looked at how to analyze the closed system, right, by hand, and now we are going to move on to analyzing the system by our particular software VMINTEQ, and for this let us look at the particular values with respect to our recipe species. Let us take NaHCO3 naught is equal to 5 millimolar, and let us for the sake of ease also take Na2CO3 naught to also be 5 millimolar, right. So again here we are trying to work it out by VMINTEQ, and we are saying that both our recipe species or the compounds you are putting in or adding to the solution initially, which is NaHCO3 and or which are Na2HCO3 and Na2CO3, are both equal to 5 millimolar concentration, right. So again, before we plug in VMINTEQ, right, we always want to understand or try to predict the species, or at least certainly the pH. So let's try to take a call on that. So keep in mind that we are adding HCO3 and I believe CO3 2 minus, sources of HCO3 minus and CO3 2 minus, and we are doing that at relatively the same concentration, right. So more or less we are adding the conjugate acid and base, right. So we are adding that at the same concentration. The key is that we are adding them at the same concentration. So thus what would you expect, that the pKa would be equal to the pH, right. As we know, when the protonated form and the deprotonated form are at equal concentration, when is that? That is only going to be the case when pH equal to pKa, and I think the pKa was around 10.2 or 10.3. So let us see where we are going to be, right. So first we need to define our H total, and that I believe is equal to NaHCO3 naught, right, and that is going to be equal to 5 millimolar. And what is our CO3 total? That is going to be equal to NaHCO3 naught plus Na2CO3 naught, and that is going to be equal to 10 millimolar. And the sodium, total sodium is going to be equal to NaHCO3 naught plus 2 times Na2CO3 naught. So that is going to be equal to 15 millimolar, right. So 5, 10 and 15. So now let us plug this in into VMINTEQ, and here we have pH to be calculated from mass balance, ionic strength to be calculated. So I will use the units as millimolar, and first we are going to add H plus, or I guess initially we have C here, so we are going to add CO3 2 minus, and we believe we had that to be 10 millimolar concentration, right. So I will have that at 10 and add that to the list, and next up should be H, and that we said was going to be equal to 5 millimolar. So that is going to be 5 millimolar, and we have sodium, and that we said was going to be equal to 15 millimolar, and that is going to be added to the list. So let me check or confirm that all the three are the relevant concentrations that we want. So the three components were H at 5 millimolar, CO3 at 10 and Na total at 15, right. So we are on the right track, and I am going to go back to main menu and run VMINTEQ, and so obviously the pH is now nearer to the pK value of 10.2 or 10.3. So that is something we are fine with, and we see that we have different concentrations here, right. And one reason why the pH might be slightly off is that the ionic strength is relatively high. So that is going to affect your particular concentrations, and that is what you see here, I guess 4.2 here and 2.4 here and so on. And more importantly, let us look at the species distribution. What will that give you an idea about? It will tell you in what forms or in what percentages is CO3 total or CO3 present as. So it looks like it can present as we know, CO3 2 minus, HCO3 minus, right, and looks like nothing will be present as H2CO3. Why is that? Because the pH is 10.7. So looks like 42% is present as CO3 2 minus, right, and 51% is present as HCO3 minus, and one particular species that we missed was NaCO3. I believe that the Ka value for this, or the equilibrium constant for this, would be relatively less or negligible, but that seems to be a minor error there, or minor assumption that should not have been taken. So anyhow, VMINTEQ confirms this, so that we have 42% as CO3 2 minus and 51% as HCO3 minus. And why do we have slightly higher concentration of HCO3 minus compared to CO3 2 minus? That is because the pH is 10.07 and the pH is 10.07 and the pKa is 10.3, right. So which one will predominate now? The protonated form will predominate, and the protonated form in this case for that pKa2 is HCO3 minus. So HCO3 minus is at a slightly higher concentration, right, and then compared to the CO3 2 minus concentration, and I believe that is what we are going to see here. HCO3 minus is slightly higher than CO3 2 minus, right. And I guess with that we will be done with today's lecture session. So, in the next lecture session or couple of lecture sessions anyway, we are going to try analyze the open system, right. And with that I will end my session for today, and thank you.